Hey guys, this week we're going to look at polynomial functions. So last week we looked at polynomials in general. Now we're going to narrow that down specifically to functions, okay? So throughout these lessons I'll probably just say polynomials, but whenever we refer to polynomials from now on pretty much, it's going to be talking about specifically polynomial functions. So this is the general form of a polynomial function. It's got a bunch of coefficients and exponents, and it's just a bunch of monomials added together. Now notice they're all x. You're only going to have one variable. That's the main difference here. For example, a circle, it's got x's and y's in it. It's still a polynomial, but it's definitely not a function. By limiting to one variable and with specific exponents, we have functions, polynomial functions. So all your coefficients, they have to be real numbers, no i's. Your leading, oh shoot, I gave it away. The leading coefficient, the first one, cannot be 0. If it's 0, well, it could be any degree, right? If you just stick 0 times x to 1 million, it could be a millionth degree. It doesn't work like that. So it's your first non-zero coefficient. Another thing, your exponents, they must be positive and integers. No fractions, no negatives. So if you remember a fractional exponent, that's a radical, a root. So a square root is a 1/2 power. You can't have that. No square root of x, no cube root of x. No fractional exponents and no negative exponents. You can't be reciprocating things. If you remember the reciprocal mother function, that weird thing that had those asymptotes, yeah, can't have that. But again, a sub n is the leading coefficient. I spelled that right. It's right there if you, yeah. Let's look at some examples. And we're dealing with x for our variable here. So x is to what power here? There's no x. Anything to the 0 power is 1, so this is a 0 degree. If you're in standard form, that is in descending order, the first coefficient is your leading coefficient. Well, it's the only dang one here, so it's 4, obviously. Now this one, it's linear, yes, that's correct, but what is the degree? The degree is 1. What's the leading coefficient? -5. Do not forget your negative. That is paramount. Next one, it's in standard form, degree is 2, leading coefficient is 12. Degree is 3. What's my leading coefficient here? Negative. Well, just negative can't be a coefficient. Don't forget there's an understood coefficient of 1 here. It's a -1. The coefficient is 1, not x. X is not freaking 1. X is a variable. It changes. Leading coefficient here is -3. Degree is 4. Degree is 5. Leading coefficient is 9. Not too terrible, right? With this information, we can imagine what the graph will look like in general, at the big picture of it. Not the specifics, but the big picture. We can kind of see just by these two pieces of information, the degree and the leading coefficient. We're going to get there. Let's think back to our mother functions. So the constant mother function, the flat line, y equals a number, or f of x if you want to use function notation. I'll just go with y equals a number. Let's give it an example. It could be any number. Let's go with 4 because they did that earlier. And remember, a constant function is a horizontal line. There. Linear. The basic linear mother function is y equals x. Slope of 1, y-intercept of 0. And here's that one right there. So I'm going to try and estimate it nicely. something about like that. Slope is 1, y-intercept is 0. Quadratic, that's x squared. Again, we're talking about polynomial functions here. So we're not worrying about the absolute value mother function. That's, what is that? That's no degree, that's no exponent. What's going on here? It's absolute value. It's a completely different thing. Not worrying about it right now. So we're going to the quadratic next. Again, make sure you have a nice round bottom on those and a sharp bottom on the absolute values. I'm not doing that right now though. No absolute values. So they better all be round. Quadratic mother function looks about like this. Also notice we're not worrying about square root. Again, square root is a 1/2 power. Can't have a fractional exponent for polynomials, polynomial functions. Y equals x cubed. So look at your mother functions. If you have the sheet still, it's going to be coming in handy. You need to remember all that stuff. So it's looking like this. So let me try and sketch that. And again, you're just sketching here. You're not going to have to plot anything. Just give a general sketch. Now, ones we didn't look at before. The quartic and the quintic. Remember, that's just 4th degree and 5th degree. So we know what their mother functions equations will be. X to the 4th and x to the 5th. But you most likely do not know what they're going to look like, unless you played around with them before for some reason. Well, let's discover what they're going to look like. Let me introduce you to Desmos. So if you just Google Desmos, actually let me do it that way so you can see what to do. If you Google Desmos and click on beautiful free math, it'll give you some options. Eventually, my computer will load. Sorry, I have bad signal in the closet. So first thing right here is graphing calculator. We go to math tools. I'm not sure what's here at the moment. Got graphing calculator, scientific calculator. So yeah, these are the two you probably want to use. I think this one's kind of nice. I think it does fractions for you. We'll just take a look at it for a second. This is an aside, I guess. Yeah, it's got your exponents and absolute value. Fractions, nice. And it has them nice and neat for you. And it can convert it to a fraction. So if you don't have the Casio FX115ES Plus, you can use this, and it's not terrible. But we're interested in the graphing calculator. The Casio FX115ES Plus is not a graphing calculator, so it cannot graph for you. Still give you a table, but I'm not going to worry about that. What on earth does y equal x to the 4th look like? Huh. Well, that kind of looks like the same thing as that. It's a little skinnier, I guess. It's got a flatter butt. I don't know, but they look pretty much the same. Oh, oops, wrong button. Huh. What if I do that? Huh. Interesting. You might see where this is going. Those are not vertical lines, by the way. It's just because we zoomed in so much they look like that. But x to the 4th looks pretty much like a parabola. So let's go draw that. Oops. So x to the 4th looks almost the same as a parabola. What do you think x to the 5th looks like? Pretty much like a cubic, but a flatter midpoint here. Not midpoint, because it's long, it goes on forever, but middle section. Something like that. Okay, let's see what they're going to ask next. Okay, so now we get to play with end behavior. That's what I was going to look at too. Remember how I told you we could see what the big picture was just based on the degree and the leading coefficient? Well, that's called end behavior. You might be thinking, but it goes on forever, it doesn't have an end. Absolutely right. But you can't draw forever, so eventually you're going to have to put some arrows on there, right? So our end behavior could be up, down, constant. That's about it. Or non-existent, I guess, if you're looking at square roots. That's not worry about it. It's either up, down, or flat, but it won't be flat for polynomials. So here's how we write it formally. As x goes to infinity, f of x, that's the y values, goes to, and you either put positive infinity, negative infinity, 0, whatever it goes to. End behaviors could be constant too if you have asymptotes. We will not, because we're only dealing with polynomials. Polynomial functions, don't forget. 4x to the fourth, 6x cubed minus x. 4x to the fourth. I'm using shift 6 for that, by the way. You can also use this little pop out here. 6x cubed minus x. So this thing. Got a bunch of random things here. We'll talk about each of these in due time. But for now, we're just looking, what does it look like as x gets really, really freaking big? And what does it look like as x gets really, really freaking small? Let me zoom out just to check. Well, I think it's going up. Yeah, it's still going up. And it's still going up. And I can't even see it anymore, but yeah. So as x gets really small, it's going up. As x gets really big, it's going up. Interesting. So up is positive infinity. Let's look at number 2, negative x squared plus x. Zoom out. I think it's going down for both of them. Yeah, it's still going down. Yeah, it's going down, right? It's down. So that down would be negative infinity. Here we're looking at the y value specifically. Okay. 2x cubed, let's check that one out. And notice you do not have to put the y equals. You can, though. Can you put f of x if you want to? I forgot what my numbers were. 2x cubed. Oops. That's it. That's it. Okay. This looks like it's going down as it gets smaller and up as it gets bigger. Yeah, I think so. Yeah, you can kind of see as x goes to the left, it gets smaller. As x goes to the right, it gets bigger. So as x gets bigger, your function gets bigger. As x gets smaller, your function gets smaller. As x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. Negative x cubed is next on the list. Oh, that one looks backwards. Huh. Yep, I think it's backwards. As x goes to infinity, we're going down, negative infinity. As x goes to negative infinity, we're going up, positive infinity. Negative 2x squared plus 4x minus 7. That was a lot. Squared plus 4x minus 7. Yeah, that. So let me go home. Oh, let's shift it down here. Let me scroll up in here. Looks like it's going down. Let's check it out. Down. Yep, it's going down. So negative infinity, negative infinity. Let's check this one out. Half, ooh, a half. X cubed plus 7. And let's go back to home. Let's shift it up 7. Obviously, you should know that because you're familiar with your mother functions, and that's a vertical shift. And that would be a stretch or compression, depending on how you're looking at it. If it's outside the function, so that would be a vertical compression. But yeah, it's all come back. You don't have to remember that. You can use decimals now. It looks like it's down and then up. Let's see. Let's go out. Yeah. As x gets smaller, y gets smaller. As x gets bigger, y gets bigger. So infinity and negative infinity. Did you notice a pattern? Well, let's compare them. Sometimes they're different, and sometimes they're the same. If they're the same, look at your degrees. They're even. And if they're different, your degree is odd. So the parity of your function determines whether it's going to be the same direction or opposite. Now, if you think about your basic mother functions, x squared, it's like that. But if you have a negative out front, so a negative leading coefficient, that's going to reflect it over the x-axis to that sort of thing there. So if you have a positive leading coefficient and an even degree, it's going to go up and up. Actually, I'm going to draw that kind of. And it's, it's like this, right? So let's do a line kind of like that and like that. Now, if it's even degree but a negative leading coefficient, that's going to reflect it over the x-axis. It's going to look something like that. Now, if it's an odd degree, remember your cube mother function, it's going down and up. So down, then up. And if you think about reflecting that, it's going to be up and then down. That's it. That is in behavior. Okay. So, looking at these two pictures, we're going to decide, is it even degree or an odd degree? Is it a positive or a negative leading coefficient? So let's look at it. Looking at the end behaviors, it's down and then down. Well, that's got to be even because they're going the same way. So it's even. And then I guess let's stick that in here. Your basic mother function is up, right? So that's got to be reflected. So it's negative leading coefficient. So negative leading coefficient, even degree. Now, I bet you could be a little bit more specific. What is the minimum degree this thing could be? How on earth am I supposed to know that? You know. It's got 1, 2, 3, 4 intercepts, right? Well, if you got x squared, that has at most 2 intercepts. If you got x to the 4th, that has at most 4 intercepts. Now, it could be 4 or it could be 6, which has at most 6. It could be anything 4 or above. But if you look at that, you know it can't be a square. There's no way that's a quadratic. And I'll be back in a bit. All right, I'm back. So this one had an even degree with a negative leading coefficient, so it's down, down. This one is down and then up. Well, it's opposite, so you know it's an odd degree. Think back to your basic cubic mother function. Remember that one, you're good. Remember your two basic cubics and quadratics, you got this. Down and then up, well, that's how it normally goes, so this is definitely a positive leading coefficient. Look back at your cubic mother function. It's down, then up. And that's, x cubed, it's positive. So this is down, then up, that's positive. And if we look at this one, it crosses 3 times, so all we can guarantee is that it's at least a 3rd degree polynomial. Can't say for sure it's 3rd. It could be a 5th degree and look like that. We don't know. We just know for sure it's at least 3. We'll get there. Turning points. Okay. That's whenever it switches. It's going up, 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 then it's going down. That's a turning point. Right here. It's going down, 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 then it's going up. Right there. These are turning points. If the turning point is higher than the nearby points, it's called a relative maximum. Because it doesn't necessarily mean it's the maximum of the graph. It's higher than the ones on either side of it. Then it's a relative maximum. Or also sometimes referred to as a local maximum. Oh, I'll be back in just a minute again. Hang on. Okay, I'm back again. Apparently Alana sneezed and we didn't say bless you. So, back to business. So I don't care if you use relative maximum or local maximum. They both mean the same thing. You could, see it either way when you get to college. Doesn't matter. If the turning point is lower than the nearby points, it's called a, can you guess, either a relative or local minimum. So relative minimum, yeah, I can't type, or local minimum. Now the absolute maxes and mins, we abbreviate them with max and mins, would only occur if we had an even degree. Otherwise, they're all going to be local. You can have more than one local. Like you could have 5 local minimums. But you can only have one absolute maximum or minimum. And if you have an odd degree, you won't have any absolute max or mins because they're going to go up and down. Anyway, maximum and minimum values are called extrema. They're extreme values, so they're called extrema. So the turning points define where your function is increasing, that is going up, or decreasing, that is going down. One more time, let me pause it. Okay, so that was just your former teacher being silly. Back to business here. So let's label these. If we look at this, you'd think that's a maximum or a minimum. Well, on either side of it, the points are lower, so this is a maximum. So this is a local maximum. I mean, it's local because it's shorter to type. Doesn't matter. You could say local or relative. I'll take either one. And this one, the points on either side are higher, so it's a minimum. Local minimum. It's the lowest value around. Nobody's smaller than that thing. Okay. Now why? She unplugged my charger. Why did she unplug my charger? I don't know. I got 73%. I should be good for the rest of the video anyway. Find the turning points, yada, yada, yada. So we're going to plot this on Desmos. So don't worry about these. You're going to just graph it on Desmos. And then you're going to literally just read the values off of it. Now, you have to be very specific as to what you put as your answer, because the questions can be very specific. If it asks for the maximum value, that would be the y value. If it asks for the location of the maximum value, that would be the x value. And if it just says, what's your maximum? Put the whole dang point. So let's go back to Desmos. And just type that in there. X cubed, I said cubed, minus 6x squared. I typed something. There we go. plus 7x plus 2. Boom. Okay, you can go back up now. And let's just go over here. Okay, so if we look at Desmos, I'm going to go ahead and go over all the pieces that it gives you, because you're going to see a bunch of dots here. I got it out there, I got it out there, and I got that there. What are those? You know what those are. Tell me what those are called. Yeah, I can't hear you. This is a video. Jeez. Those are your roots, your solutions, your x-intercepts, all those things. That's the answers whenever you set it equal to 0. That's what those are. Okay. What's that? Again, I can't hear you. This is a video. This is your y-intercept. This is your y-axis. That's your y-intercept. And finally, we've got these guys. Well, those are your extrema, right? So that's what we're going to be looking at. So yeah, this tells you, these are your instructions if you're on, say, a TI-83 or 84. That's how you do it on there. But if you're on Desmos, you don't have to do anything. It automatically plots them for you. So we're going to get these, and we are going to use all 3 decimal places. So if it's, got 4 of them round to 3 decimal places, we're just going to use 4. We're just going to use 3. So 0.709, 0.4303. I'm going to do this. I'm bad at remembering, so I'm going to do that. And I'm going to do that. Any hour now. There we go. And also, so if we look back at the graph, this 0.709 for the x is our, well, it's higher than the other 2 pieces. That's a maximum. 3.3-ish, that's our minimum. Maximum. Minimum. So apparently your book likes relative. REL, period, that's abbreviated for relative minimum or maximum. Don't care. Again, you can say local or relative. And you could see it either way too, so know both. Now, this is interesting. It's asking about increasing and decreasing intervals. Okay, for some reason, people get confused here. I do not know why. Well, what country are we in? We're in America. So if you're in America, how do you read? Left to right. That's how you read a graph also. So if I'm going from the left to the right, it's starting out going up. It's going up until I get to this turning point, our maximum here. So from negative forever to this maximum dot right here. It's going up. So we are going to put this in interval notation. Actually made it a little bit thinner there. Now, I like to do this, just on a fluid thing. I'm going this way, and I'm going, my next piece is decreasing, and I'm increasing again. Some people like to break it up. I'm increasing here and here. That's a good way to miss stuff, in my opinion. So I'm going to go with these, this decreasing piece next. Well, it's the x coordinates my maximum and my extrema, right? So it's this place to that place. Now, we're talking about going up and down. So you don't care what the y values are. You're just looking at the location of those turning points. You're just looking at the x values. And then, of course, after this dot, you're going up forever. So I have to increase again, usually separated by commas. you might see the, the union symbol could pop back up here, but I'm gonna go with commas to separate our intervals of increasing and decreasing. Just if you really want to use the union symbol, feel free. But first year of college, whenever you're in my math lab, you better read very carefully, because you put a comma and it wants a union symbol, it's gonna mark it wrong. Put a union symbol, wants a comma, it's gonna mark it wrong. So just pay attention to the directions. For me personally, don't care. Enough yammering. 3.291. Again, we're looking at the location of those turning points to infinity. Next. We've got a few examples here. I'll do half of them, I guess. Let's see what we got. Okay. So this one was an odd positive. Let me do an odd negative. We'll do this one. Right now, without doing anything at all, you should know the answer to this. Domain. It's a polynomial function. So your domain is all freaking real numbers, period, no exceptions, no ifs, ands, no buts. That is your domain. Now, what's your end behavior? It's a freaking odd degree, and it's negatively in coefficient. That's up and then down, without even looking at it. This is also negative infinity to infinity. If it's an odd degree, both domain and range are negative infinity to infinity. If it's an even degree, domain is, but your range is not. Relative maximums and minimums. Oh yeah, your direction, you can kind of ignore those. We're gonna, instead of graphing them with the table, we're gonna graph them with decimals. Negative x cubed plus 3x squared. Now that's simple squared. So again, we've got our extreme right here. And notice that's almost all we got. We also got this dot right there. Whatever dots they have on here, go ahead and transform over here. So 003024. 003024. And then kind of make this shape-ish thing. So I'm gonna do this. Looks like -1, 4 is also a thing. So I'm gonna try and go later. Dude, that's gonna be tough. As long as this general shape is fine. Get those important dots, you're good. There. Now, this is the hard part. You gotta come up from here and go down here. There. Boom. Perfect. Beautiful. Gorgeous. It's done. So I'm actually gonna make my points a different color so I can distinguish them. I probably hope you did the same. So, what are my relative maximum? 2, 4. That's the only one. Minimums 0, 0. That's the only one. What is my location of maximum? 2. What's the value of my maximum? 4. Keep that in mind. And behavior up and then down. So as x gets really freaking big, we're going down. Yes, as x gets really freaking small, we're going up. And I can read from here what my interval of increasing is going to be and what my interval of decreasing is going to be. Again, you're American. Read left to right. If you're not American, I don't care. Read left to right. That's how we read math. So going from left to right, we're going down, 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 down until we get to the 0. Again, we're looking at the x values here. So I'm decreasing from negative infinity to 0. All right. Up, 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 up. 0 to 2 is where I'm going up. Down, down, down. 0 to, oh wait, I'm still going down. You don't care about where the intercepts are. Again, your turning points are your extrema, your maxes and your mins. That decides your intervals of increasing and decreasing, not your roots. This doesn't matter at all. Just because there's a point on there doesn't mean you have to stop there. Keep going because it's not changing, is it? So from 2 to forever, we're going down. We're decreasing. Again, I'm going to use a comma. Okay. So let's see. Not too bad. What's the next one? Maybe, no. Okay, I'll do one of these. I mean, you should be able to get the idea here. This one's got a negative. Let's do it. Okay, we're back. That was weird. Here we go again. Okay. I can make another myself to just go and chop that little piece off of this. I had a children, but whatever. What have you? I think I typed that in correctly. Hopefully I did. So here we go. We got all kind of dots on here. Now you don't need to label them. You just need to put them. You don't even have to put them all. It's fine. Now these extrema, we do need to put. We have one max, two maxes, and a min. We have two maximums this time. La 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 la. This intercept just go somewhere between -2 and 3. That's fine. -2 and 3, like there. And then -1.5 and 6.5 ish. -1.5, 3, 6.5 ish, somewhere in there. Then -0.5, 0, pretty much. 0, -2. This one, almost a half, -2.5. There, a little over 1, and then almost -2. A little over 1, almost to -2. So I'm going to stick it right there. And then just, where's this at? Oh, already got that. So there, I think I have all the dots. Now let's connect them. Let's just look at something like, oh, that was cool. I missed. So try and do better than me. Yeah, it's like a drawing anyway. And something like that. Boom. So if you have all those dots, it kind of helps you draw it. So probably would be the first thing I'd do would be to sketch this thing. Just sketch it. But of course, you know the domain for every single little polynomial mother function. Well, not mother function, I guess polynomial function. All of them. Domains are real numbers. Period. Now for this one, it's an even degree. Jesus. All right. So it's going down forever, but it stops up here at this value. So it's -infinity all the way up until I get to wherever this point was, which it was 6.494. 6.494 ish. Now, It's a solid dot, right? It's a solid dot. Include the thing. The bracket. Interval notation. All right, we've got two relative maxims. I'm just going to separate them with commas. I got this one. I'm just going to be lazy and take a picture. And this one. And if you're confused as to what's what, you can unclick everything else. And those are your two maximums. See, they're solid black dots. And my minimum is this one. That way you can make sure you grab the right thing. I would write them down, but I have a terrible memory, so this is actually faster. That's one. That's this one right here. That's this one right here. It's another small one. And this one right here. The order you put them in does not matter in the least, as long as you put your maximums with your maximums and your minimum with your minimums. So this guy's my minimum, these two are my maximums. In behavior, it's down, down, so that's negative infinity both ways. Interesting note, on my math lab, they will have you poking arrows. So you have multiple choice, and like this would be the option to click. It would look something like that. It actually have arrows instead of this interval, this infinity notation here. Okay, since I have my maximum and minimum values right here, the turning points are listed for me. So I don't have to go back and forth and jump because I know what the numbers are going to be. Starting at negative infinity, going until right here, negative 1.574, I am increasing. It's going up. Increasing and decreasing are always parentheses. Just let's throw that out there. We don't include these values because at this maximum, is it going up or is it going down? Yes, no, I don't know actually. It's not going up or down, it's a point. Points don't go up and down, it's just there. Anyway, negative infinity all the way up to negative 1.574. And yeah, that should be enough room. Should be able to fit this. Decreasing next from this dot right here, negative 1.574. All the way until, oh, I got a point, I gotta stop. No, you don't. I got a point, I gotta stop. No, you don't. I got a point, I gotta stop. Oh, yeah, you're changing right there. 0.409. And then I'm going up from this little itty bitty piece right here, 0.409 to 1.164. 1.164. Yeah, that number. Let's see if we can squeeze that in there. 1.164. Cheat a little bit, move my paper over a little bit. Okay. And then I'm going down after that, the comma, 1.164, all the way to forever. I'm going down after that. All right, guys, there's not much else to tell. It's use Desmos. Lots and lots of practice with Desmos is all you got to do. today. See ya.